Let's look at some examples of strongly well-posed problems. We proved that a strong well-posedness that is stable under lower order perturbations implies strong hyperbolicity or Petrovsky parabolicity. And one big class of strongly hyperbolic systems is actually symmetric hyperbolic systems. And symmetric hyperbolic systems are given by this form, where these matrices A1 through AN are Hermitian. If they are real, it means that they are symmetric. So I'm not going to give a proof. Proof is given as an exercise. So one example would be just the wave equation. Let's write the wave equation in symmetric hyperbolic form. So in particular, we need to have one time derivative on the left hand side, and on the right hand side we need to have just first derivatives. So we introduce new variables called the time derivative of u w0 and the space derivatives wk. Then this wave equation, the original wave equation, can be written in like this, and from the definitions, from this definition, we can write the time derivative of those wk's are actually the space derivatives of omega w0, or just the gradient of w0. And to see that this is really a symmetric hyperbolic system, let's write this when n equal to 2 explicitly in matrix form. So for w0, you see that we have it involves only the first x1 derivative of w1. So we have this matrix here, and then x2 derivative of w2, so that we have this row. Now for w1, the time derivative of w1 is equal to x1 derivative of w0. So the second row will have only non-zero entry here, and the third row will have only non-zero entry here. And as we can see, this is symmetric, and this matrix is symmetric, so it's symmetric hyperbolic. Now, once we written in this way, we know that any lower order perturbation should be also strongly well posed. So let's look at one arbitrary lower order perturbation of the wave equation. So general lower order perturbation, as far as constant coefficients are concerned, will look like this. And you can see that, so time derivative of u, that is w0, and here the gradient of u, so that's w vector. And our equation, you can write the equation in this way, because on the left hand side you have time derivative of w0, and here that would be just divergence of w, which is also here. And the lower order perturbation becomes this, so that there is no derivatives at all. For w, so this equation is just here, gradient. But now we need to add one more equation, because there is this u here. Before, for the wave equation here, there was no u by itself. So we could actually write the equation in terms of w0, w1, and w2. But now we need to introduce the equation for u itself, and that would be just a definition. So the time derivative of u is equal to w0, and as you can see that the x derivatives of w0 or anything or any other variable is missing in the equation of time derivative of u. That means it's not going to affect those matrices, or you will just add 0 row here and 0 column corresponding to the unknown u, and this w0 will act as a as lower order perturbation, or zeroth order perturbation in this case. So it immediately gives us the result that any lower order perturbation like this is going to be strongly well posed for the wave equation. More generally, we can consider symmetrizable systems. Now symmetrizable means, okay, we have the same form as before, but instead of assuming that these matrices are symmetric or Hermitian, we are allowed to have one Hermitian positive definite matrix M that turns these matrices into Hermitian matrices when you multiply. So we assume that MA1 through MAN are Hermitian, and this is also strongly hyperbolic. And you can also think of this in a slightly different way. You multiply this equation by M from the left, then you're going to get M time derivative of U here, and over here we have symmetric matrices. So if you write those matrices as B1 through Bn, we can also recognize symmetrizable systems by this form. It's sometimes also called just symmetric hyperbolic systems when you have M in front of symmetric positive definite matrix in front of the time derivative. Okay, the next set of examples is strictly hyperbolic systems. Now we look at the symbol of the right hand side. So the symbol of the right hand side would be this here, and we require that for any non-zero psi, the symbol will have n distinct real eigenvalues. This is called strictly hyperbolic systems, and these systems are also strongly hyperbolic. Again, we are going to skip the proof. Proof is not very hard. And more generally, we have hyperbolic systems with constant multiplicities. Now, this means that the principal symbol of the right hand side has real semi-simple eigenvalues with constant multiplicities. So you can see that the strictly hyperbolic systems are special cases of systems with constant multiplicities, where the multiplicities are 1. So we are now going to discuss some examples of parabolic problems. Okay, the canonical example of parabolic problems is of course heat equation, and we can have any lower order perturbation now that will give us strong well posedness. So this would be a general lower order perturbation, and we know that Petrovsky parabolic problems must have order even. So the next simplest case would be biharmonic heat equation, whose principal part is here, and then you can add any lower order perturbation. This is not a general lower order perturbation, it's just just an example. So we have third order term, second order term, and so on. So that this would be strongly well posed. And then we want to look at one class of examples which are actually not covered by the theorem, dispersive equations. So let's look at these examples. So the first one is Schrodinger equation. Here we have the principal symbol of the right hand side minus I xi squared, and you can see that this is purely imaginary, so that the matrix, this matrix here, the matrix norm will be uniformly bounded. Actually, this will be bounded by 1, and this will immediately give us strong well posedness, even though it's not covered by the theorem, because we can perturb it by first order operator to make it not strongly well posed. So, but by itself, this problem is strongly well posed. The next example is so-called Airy equation. It's a third order equation. Again, the symbol of the right hand side is purely imaginary, so again it's strongly well posed. And we can see this is third order, so for example we can perturb it by a backward heat operator to make it not strongly well posed, but by itself is actually it's strongly well posed.